Tonight, we were sliding past the usual friendly stars and easing our focus way, way out into the dark, cold velvet that wraps around our solar system. You're settling in, maybe pulling that blanket up under your chin, and you look up at the familiar ceiling of the cosmos, the one with the friendly, dependable sun right in the middle, pouring out light and warmth. You see the stars, distant and sparkling, but you trust the quiet rhythm of our own star. But what if that warm, reliable light you count on wasn't alone? What if the sun, our single, perfect sphere of fusion, was actually part of a binary system? A secret couple? A stellar pair locked in a dance so slow, so long, that its partner is practically invisible, lurking in the deepest shadow? Imagine a vast, lonely space, colder than anything you can conceive, kilometers past the last flicker of sunlight. You float there, suspended, and you look back at our solar system. It's a bright, welcoming beacon in the void. Now, you slowly turn your head, and in the opposite direction, in the inky blackness, you start to perceive something else. A flicker. Not a star, not a galaxy, but a tiny, distant, slow-moving point of deep red or even infrared light. It's hard to see, radiating almost no visible heat, but it is massive. It is gravitationally potent. It is the sun's secret twin, and you probably won't survive the next time it decides to visit. It's called Nemesis, a name pulled from the Greek goddess of divine retribution. It wasn't invented by science fiction writers, but by serious physicists in the 1980s attempting to solve one of the greatest mysteries in paleontology. Why does life on Earth die in sudden, violent, repeating waves? The mainstream historical fact is that the fossil record shows that life has been systematically reset, not randomly, but with a strange, unnerving regularity. Every 26 to 27 million years, the diversity of life on Earth takes a catastrophic dive. The dinosaurs were one spectacular casualty, but they were just one tick of a cosmic clock. Why does our perfectly stable planet suffer this periodic doom? The sheer mathematical rhythm of the death pulses demands an explanation that is astronomical, not geological. It requires an outside force, a pendulum swinging back and forth with a period of 27 million years. The conflict at the heart of the Nemesis theory is that our understanding of the solar system as a single, isolated unit is wrong. If Nemesis exists, it means we live in a massive, gravitationally complicated binary star system, where the second star's sole function is to destabilize our world. So, what exactly is Nemesis supposed to be? It is not another bright yellow star. It is believed to be a dwarf star, most likely either a dim red dwarf, the smallest, least luminous type of true star, or perhaps even a brown dwarf, a failed star, too small to sustain hydrogen fusion, glowing only with the residual heat of its formation. Imagine the sun as a powerful stadium floodlight. Nemesis is a dying ember, radiating just enough heat to exist, but not enough visible light to easily find. It is believed to be orbiting the sun at an immense distance, perhaps 50,000 to 100,000 astronomical units, AU. To give you some scale, the distance to Pluto is less than 50 AU. Nemesis is orbiting 1,000 to 2,000 times farther out than Pluto. It's out there, somewhere. Its gravity weak but pervasive. Its enormous orbit means it takes those 27 years to complete a single, silent, deadly rotation. And every time it swings into its closest approach, it doesn't aim for the Earth itself. It aims for the cloud of icy oblivion that surrounds our solar system. This star, if it is real, is the ultimate paradox. It is a fundamental partner to our sun, yet it is utterly invisible. It is a twin, but its existence is proven only by the death it leaves behind. The only way to find it is to understand why it's hidden. And that's our first task. We know the mass extinctions follow a 27 million year clock. We have the physics demanding a distant, massive orbital partner. So why, with our powerful modern telescopes, hasn't Nemesis been found? Why does the greatest threat to life on Earth remain a scientific ghost story? The reason Nemesis has evaded detection comes down to three crushing astronomical realities: dimness, distance, and proper motion. If Nemesis is a red dwarf, it is simply too faint. The brightest red dwarfs are already dimmer than the sun by factors of 1,000, and the coldest ones emit almost no visible light at all. If Nemesis is a brown dwarf, a failed star barely bigger than Jupiter, it glows primarily in the infrared spectrum, radiating only residual heat. Our eyes, and most of our early telescopes, are built for the visible light spectrum. Imagine trying to find a cooling coal hidden in a vast, dark field using only a flashlight. You can only detect it by the tiny bit of warmth it emits. This challenge necessitated the use of specialized tools. The mainstream historical fact here is the Wide Field Infrared Survey Explorer, WISE, a space telescope launched in 2009. WISE mapped the entire sky in infrared, looking specifically for these kinds of cold, hidden objects. The results were dramatic. WISE successfully discovered hundreds of new brown dwarfs in our general neighborhood, but it did not find Nemesis. By comprehensively scanning the sky, WISE proved that if Nemesis is a star, it must be either extremely cold or it must be much farther away than the distance. The lack of a detection only sharpened the mystery. Nemesis is either too cold to register, or it's playing a more distant, slower game. The second problem is the sheer distance of its hypothetical orbit, up to 100,000 AU. At that range, the light, or heat, reaching us is so diluted that it's nearly impossible to distinguish from background noise or instrument error. It is simply too faint to stand out. But the third problem, proper motion, is the most difficult to overcome. This is the star's slow lateral crawl across the background of distant galaxies. When you look at a star, it appears fixed, but all the stars are moving. Stars close to us move faster relative to the background than those far away. Since Nemesis is theorized to be at the gravitational limit of the solar system, it moves incredibly slowly. To track its movement, astronomers have to compare photographs of the same patch of sky taken years, sometimes decades apart. The tiny shift in Nemesis's position would be measured in fractions of an arcsecond, a measure of angle so small that it's like looking at the width of a human hair from a mile away. The conflict here is a race against time. We need years of observation to confirm this slow movement, but the object itself is likely so dim and distant that decades of work are required just to get a clear image to begin with. So, Nemesis hides in plain sight because it's dim, distant, and moves at a geological crawl. But where is it exactly? To understand its destructive power, we have to look to the place it disrupts, the vast frozen reservoir of doom that encircles our world. You're still out there, shivering in the cold, 50,000 AU from the sun, but now you have a destination in mind, the Oort Cloud. This isn't just empty space. It's a vast, icy reservoir, the true edge of the sun's gravitational influence, and it is the key mechanism through which Nemesis might destroy us. Imagine the solar system as a giant snowball. The sun is the compact, warm core. The inner planets are the tightly packed layers right around the core. Then you have the Kuiper Belt, the ring beyond Neptune where Pluto lives, which is like the dense inner part of the snowball's crust. The Oort Cloud, however, is the massive, diffuse, extremely distant outer shell of that snowball. It's theorized to extend from about 2000 AU out to as far as 100,000 AU, nearly a quarter of the way to the next nearest star system, Alpha Centauri. The sheer scale of the Oort cloud is hard to grasp. Even though it is massive, likely containing trillions of cometary bodies, some the size of mountains, the objects are spread so far apart that the density is incredibly low. If you were standing on one Oort cloud object, the next one might be millions of kilometers away. These objects are remnants scattered out from the inner solar system during the planetary formation process. These objects are now held in a delicate, nearly static orbital state by the Sun's gravity. But they are also constantly being tugged on by the gravitational fields of passing stars and the overall galactic tide, the subtle, pervasive gravitational force exerted by the Milky Way galaxy itself. And here is where Nemesis, the Sun's massive, dark twin, becomes the celestial slingshot. Its orbit is so elongated that it takes those millions of years to complete. But every time it swings into the perihelion, its closest approach to the Sun, it carves a path directly through or adjacent to the outer edge of this fragile Oort cloud. When Nemesis passes by, its colossal mass, even though it's hundreds of billions of miles away, is enough to overwhelm the subtle, ambient gravitational influences holding the Oort cloud objects in their peaceful orbits. Think of the objects in the Oort cloud as billiard balls, perfectly arranged on a giant, dark table. Nemesis doesn't hit them directly, it just shakes the entire table violently. Some comets get a sudden outward gravitational nudge and are flung completely out of the solar system, lost to interstellar space. But far more tragically for us, many of them get a gravitational push inward. The effect is not subtle. This gravitational perturbation sends vast numbers of icy bodies, some tiny, some kilometers wide, cascading toward the inner solar system. These are long-period comets. When Nemesis does its stirring, it doesn't send just one or two. It sends tens of thousands of them, creating a prolonged, devastating comet shower that could last for millions of years. The mainstream historical fact connecting this to reality is that we know stars passing through the Oort cloud do affect it. A famous example is the theory that Schultz's star, a tiny red dwarf and brown dwarf pair, passed through the outer Oort cloud only about 70,000 years ago, a cosmic blink of an eye. The open scholarly debate here centers on the eccentricity of Nemesis's orbit. If the orbit is highly eccentric, stretched out, its closest approach is more dramatic, causing a severe, short-lived comet shower. If the orbit is more circular, the perturbations might be milder but more continuous over time. Which type of orbit better explains the periodic nature of extinctions? The primary job of Nemesis is to take the latent, frozen hazards of the Oort cloud and turn them into existential threats aimed directly at your planet. The table is set. Now we watch the billiard balls fall. The gravitational perturbation from Nemesis isn't just a hypothetical shake. It leads directly to the mechanism of global catastrophe, the Comet bombardment. You've seen the table shake, now you watch the billiard balls scatter. The Oort cloud objects, those icy mountains and cosmic gravel pits, are now falling inward. This is not a gentle snow shower, this is a siege. The speed and sheer number of these objects are the defining factors of the danger. A typical long-period comet can move incredibly fast, tens of kilometers per second. If a substantial portion of the Oort cloud is destabilized by Nemesis's passage, the inner solar system enters a period of heightened risk that could last for 2 to 3 million years. The cosmic shrapnel keeps arriving long after the gravitational bully has moved on. Think about the sheer number of targets the Earth has to face. If the Oort Cloud contains trillions of objects, even a tiny fraction being pushed inward is still a devastating barrage of millions of potential threats. The vast majority will plunge toward the Sun or be gravitationally captured by the gas giants like Jupiter and Saturn, the solar system's colossal vacuum cleaners. But Earth is a relatively small target, and statistically, a significant number of these rogue comets are bound to intersect our path. The rate of major impacts, those that can cause global devastation, could increase by a factor of 10,000 during the peak of a Nemesis-induced comet shower. This is the conflict in the story of Nemesis, the slow geological rhythm of life versus the sudden, overwhelming violence of space. What exactly does a comet impact do? The impact that killed the dinosaurs, believed to be an asteroid, provides a grim template. However, comets are different from asteroids. Asteroids are primarily rocky and metallic. Comets are primarily ice, rock, and dust. When a large comet strikes Earth, the initial kinetic energy released is astronomical, creating a crater kilometers wide. The immediate effect is a massive, continent-sized earthquake and devastating tsunamis if it hits the ocean. The real global killer, though, is the aftermath. The impact blasts an enormous quantity of pulverized rock, water vapor, and sulfur aerosols into the atmosphere. This material hangs there for months, maybe years, creating what's called an impact winter. The dust veil blocks the sun, plunging the Earth into darkness, killing off plant life and freezing the planet's surface. A mainstream historical fact is that the global layer of iridium, a rare element common in meteorites, found exactly at the 66-million-year-old boundary, the KPG boundary, provides undeniable physical evidence of a massive, sudden impact causing the dinosaur extinction. This concept of a comet bombardment offers a clean payoff to the mystery of periodic extinctions. Instead of assuming one random large asteroid strikes every 27 million years, which is statistically unlikely, Nemesis provides a repeating, active mechanism. It's like shaking the apple tree every 27 million years, guaranteeing a certain harvest of destruction. The scholarly debate surrounding this is whether the observed extinctions are truly the result of impact events, or if they were primarily caused by massive volcanic activity, such as the Deccan Traps eruptions in India. Both are catastrophic, but only impacts fit the Nemesis cycle model. The statistical alignment of the extinction record, the periodicity, is what originally compelled physicists to look for an astronomical timer. Nemesis removes the randomness from existential threat. It replaces cosmic chance with cosmic inevitability. Its primary job is to turn the latent hazards of the Oort Cloud into existential threats aimed directly at us.
You've witnessed the setup, the vast, dark Oort Cloud, and the slow gravitational trigger that is Nemesis. Now you're looking directly at the payoff side of this cosmic equation, the compelling evidence connecting these cycles of destruction to the geological history of Earth. This is where the dinosaur extinction becomes not a random tragedy, but a piece of a terrifying, repeating pattern. The crucial link lies in the fossil record. For paleontologists, the history of life on Earth is punctuated by 5 major mass extinction events, the Big Five, where a huge percentage of species vanished in a geologically short period. The mainstream historical fact that launched the Nemesis theory came in 1984. 2 scientists, David Raup and Jack Sapkowski, published a landmark paper analyzing the extinction rates of marine life over the last 250 million years. Their data suggested that mass extinctions, defined as sharp, sudden drops in the diversity of life, were not random. Instead, they appeared to show a periodicity of approximately 26 to 27 million years. This discovery was the birth of the Nemesis theory. It's the scientific equivalent of finding a ticking clock buried deep inside a mountain. If you find a regular rhythm, you look for a regular driver. The Earth's internal processes, like volcanism or plate tectonics, don't typically operate on such a clean, slow, periodic schedule. You need something external, something astronomical. The dinosaur extinction, the KPG boundary, at 66 million years ago, is the most famous example, but it's just one tick of the clock. Go back further and you find the Triassic-Jurassic extinction around 201 million years ago, and then the Permian-Triassic extinction, the Great Dying, which wiped out an estimated 96% of marine species around 252 million years ago. If Nemesis is real, its orbit would be the cosmic pendulum dictating this period. Every time it swings close to the Oort Cloud, it sends a wave of comets inward, statistically guaranteeing a heightened chance of major impacts on Earth for the following couple of million years. This comet shower would then cause the extinction spike. The open scholarly debate remains fierce regarding the statistical significance of the 27 million year period. While Raup and Sapkowski found strong statistical clustering, subsequent studies using updated data and different analytical methods have sometimes weakened the signal, suggesting the periodicity might be a coincidence or a product of selective data use. The core of the conflict is this: if the cycle isn't perfectly regular, the astronomical driver, like Nemesis, is less likely, and the cause could be related to our solar system's slow, undulating passage through the plane of the Milky Way, which takes a similar amount of time. You recognize the curiosity Nemesis sparks. It takes a problem, the periodic death of life, and offers the ultimate, dramatic solution: a dark, unseen celestial twin. It transforms Earth's history from a series of random cosmic accidents into a predetermined sequence of stability and cataclysm, driven by the most distant, silent entity in our gravitational neighborhood. The fossil record whispers of a 27 million year cycle. This forces us to search for a regular astronomical timer. But if the death rate is written in the bones of ancient creatures, the physical evidence of the weapon must be written in the scars of the Earth itself. You've accepted the terrifying premise. The dark twin Nemesis stirs the Oort Cloud, sending comets toward Earth. And the geological record seems to confirm these periodic spasms of destruction. Now, you peer closer at the cycles of destruction, moving from the fossil record to the literal scars on our planet, the crater record. This is where the astronomical proof of the 27 million year clock must truly reside. If Nemesis is periodically triggering massive comet showers, then not only should extinctions happen cyclically, but the frequency of large impact events should also follow that same rhythm. Researchers in the 1980s and 90s began meticulously cataloging Earth's known impact craters and trying to date them precisely. This is a difficult task because craters on Earth erode quickly due to weather, plate tectonics, and geological activity. Unlike the Moon, which preserves every ding and dent, Earth is constantly scrubbing its surface clean. However, by focusing on the largest, best-preserved craters, those over 10 kilometers in diameter, which indicate a truly significant impactor, a statistical pattern began to emerge. When researchers plotted the dates of these major impacts, they found what appeared to be clustering around the same 27 million year intervals as the mass extinctions. This clustering of crater dates, when subjected to statistical analysis, seemed to confirm the hypothesis that an external, periodic force was at work. It offered the payoff that Nemesis theorists were seeking, a unified explanation for two separate, massive datasets: the death rate of life, extinctions, and the rate of cosmic violence, craters. The simplest astronomical explanation for a fixed, slow cycle is a massive object in a fixed, slow orbit. A mainstream historical fact underscoring this is that the crater dating has only become more reliable with advances in radioisotopic dating techniques. Scientists use elements found in the melt rock of the impact structure, like argon-argon dating, to pinpoint the age of the crater with increasing accuracy. But as the data gets cleaner, the statistical signal itself gets challenged. This leads directly into the ongoing open scholarly debate. Is the clustering real, or is it an artifact of incomplete data? Many skeptics point out that the number of large, well-dated craters is still relatively small. If you're missing half of the real impacts because they fell into the ocean or have been subducted under tectonic plates, your statistical pattern could be wildly misleading. Furthermore, the errors in dating can be significant, sometimes by a few million years, which is enough to smear the clean 27-million-year signal. The debate is often fierce, with statisticians arguing over the p-value of the observed periodicity, the probability that the pattern is simply due to random chance. If the probability is too high, then Nemesis is unnecessary. You realize this is a classic scientific curiosity, a beautiful, elegant theory, Nemesis, built to explain a striking pattern, periodic extinctions and impacts. The problem is that as the data improves, sometimes the striking pattern weakens, or alternative explanations emerge. The crater record provides the geometric proof for the Nemesis theory. If the comet shower is happening, the evidence must be written in stone across the planet's face. But the writing is blurred by time, making the dark star's existence depend on a statistical argument.
You've been tracking the ghost star Nemesis, a theoretical twin in a wide, slow orbit. But before Nemesis can be confirmed, we need to place it in context with the very real and well-understood reality of binary star systems. Nemesis is terrifying because it's a wide binary, but most stellar companions are much cozier. The curiosity here is realizing that our Sun might be an anomaly. More than half, and perhaps as many as 75%, of the stars in our galaxy are actually part of multiple star systems. Being alone is a minority state for a star. These companions come in vastly different flavors, and understanding them helps define just how weird and how dangerous Nemesis would be. We can categorize these systems based primarily on their separation distance and the type of stars involved. 1. Close binary systems. These are stars that orbit so tightly they are often less than the distance between the Earth and the Sun. They might complete an orbit in mere hours or days. The gravitational forces are so intense that they can actually exchange material, with one star stripping gas from the atmosphere of its neighbor. A mainstream historical fact is that the most famous of these systems is Algol, known as the Demon Star, which is an eclipsing binary that dims visibly every few days. 2. Visual binary systems. These are systems where the two stars are separated by enough distance that a telescope can resolve them as two distinct points of light. They have periods ranging from years to centuries. An example is the familiar Castor in the constellation Gemini, which is actually a system of 6 stars in a complex hierarchy. This is the extreme end of the scale. These companions are separated by thousands or tens of thousands of AU, making their orbits take millennia or even millions of years. This is where Nemesis falls. Stars this far apart are only barely gravitationally bound. Their long, loose orbits make them highly susceptible to the gravitational influences of the galaxy itself, which can easily perturb or even unbind them entirely. If Nemesis is real, it's most likely a red dwarf or a brown dwarf. The conflict Nemesis introduces is that its very existence as a wide binary at the edge of the Sun's gravitational sphere of influence is inherently unstable. If our solar system had formed with Nemesis in a tight, close orbit, the inner solar system would have stabilized long ago. Because Nemesis is so far out, it sits right in the gravitational sweet spot, strong enough to hold on to the Sun, but weak enough that the galaxy's pull and its highly eccentric orbit mean it only disrupts the Oort Cloud periodically. The open scholarly debate here hinges on how wide a binary system can actually be before the stars are unbound by the galactic tide. The galactic tide is the sheer gravitational force exerted by the entire mass of the Milky Way, which acts to pull widely separated stars apart. If Nemesis is truly 50,000 to 100,000 AU out, the galactic tide is immense, constantly working to steal Nemesis away from the Sun. Some theoretical models suggest that a binary system that large is unlikely to survive for the full 4.5 billion year history of the solar system. This instability is the single biggest argument against the Nemesis hypothesis. Nemesis is a star with 1 foot inside the door of our solar system and 1 foot outside. It is the unstable partner, whose chaotic, divided loyalties are felt only once every 27 million years.
You've established the parameters of Nemesis's terrifying orbit, but the ultimate mystery remains its speed. You must grapple with its almost unbelievable velocity, a crawl that dictates the timing of global destruction. If Nemesis is the driver of the 27 million year extinction cycle, then its orbital period must be exactly that, approximately 27 million years. We can work backward from that period using a simplified version of Kepler's third law, which governs how objects orbit each other. The calculation yields an average distance of between 90,000 and 100,000 astronomical units, or AU. To put that into perspective, the closest known star system to us, the Alpha Centauri complex, is about 270,000 AU away. Nemesis is hypothesized to be orbiting at about a third of that distance. Nemesis is the outermost member of our solar system, sitting just inside the gravitational boundary where the Sun gives way to the galaxy. Now consider the velocity of a star at that distance. Since the orbit is massive and the time is millions of years, the velocity of Nemesis is painfully slow. At its most distant point, aphelion, Nemesis would be crawling at a speed that is barely faster than the movement of distant background stars, making its detection through proper motion nearly impossible. However, the Nemesis theory relies on an elliptical orbit. If the orbit were circular, the star would always be 90,000 AU away, and its gravitational stirring of the Oort cloud would be constant, not periodic. To cause a catastrophic shower every 27 million years, Nemesis must plunge in relatively close to the inner Oort cloud edge, perhaps 30,000 to 40,000 AU, and then swing out to its approximately 100,000 AU aphelion. At perihelion, closest approach, its speed would be at its maximum, while still incredibly slow by human standards, maybe 0.5 to 1.0 kilometers per second relative to the Sun. It would be fast enough to register over a decade of observation if we knew precisely where to look. This orbital geometry is the source of the curiosity. It explains why we might not have found it yet. If Nemesis is currently at its aphelion, it's not only at its dimmest and coldest, but it's also moving at its slowest, making years of observation necessary just to measure its tiny change in position against the distant galaxies. And mainstream historical fact that validates this type of orbital geometry is the existence of long-period comets themselves. Their orbits are incredibly elliptical, plunging toward the sun from the Oort Cloud and then swinging back out tens of thousands of AU. Nemesis is simply a star that happens to share this highly elongated orbital pattern. The open scholarly debate revolves around the orbit's stability. If Nemesis has an orbit this wide, it is highly vulnerable to being captured by or perturbed by passing stars in the galaxy. The consensus among dynamicists is that an orbit this wide is not stable over the age of the solar system. Nemesis should have been stripped away by the galactic tide by now. This instability is the single biggest argument against the Nemesis hypothesis. Nemesis is a star teetering on the edge of two gravitational masters, the Sun and the galaxy. It is either a temporary visitor that has simply been lucky to remain bound to the Sun for so long, or it's a permanent fixture that challenges our understanding of how such wide, unstable binary systems can survive.
You've established the parameters of Nemesis's terrifying orbit, but the ultimate mystery remains its identity. Is it a dim, faint red dwarf, or something even stranger and darker? Now you delve into the idea that Nemesis might be a brown dwarf, and how this status ties into the even larger cosmic puzzle of dark matter. Recall that a brown dwarf is often called a failed star. It's an object that is too big to be a planet, at least 13 times the mass of Jupiter, needed to fuse deuterium, but too small to be a star, needed less than 80 times the mass of Jupiter, needed to fuse hydrogen. These objects barely glow, radiating mostly heat in the infrared spectrum. If Nemesis is a brown dwarf, its extreme lack of luminosity perfectly explains why we haven't found it yet. It's the ultimate master of cosmic camouflage. The curiosity surrounding the brown dwarf possibility grew stronger after deep sky infrared surveys like WISE began confirming a surprising abundance of these objects in our galactic neighborhood. The universe is littered with them. If Nemesis is a brown dwarf, its mass would still be sufficient to gravitationally perturb the Oort Cloud. Even an object only 20 or 30 times the mass of Jupiter, a heavy brown dwarf, would be massive enough to shake the icy shell when it makes its closest approach. This brings us to the fringe, yet compelling link between Nemesis and the larger cosmological enigma, dark matter. Dark matter is the invisible, mysterious substance that makes up about 85% of the total mass of the universe, and we only know it exists because of the gravitational effect it has on visible matter. One early candidate for a type of dark matter was macho, massive, compact halo objects. Machos are essentially dark, massive objects like black holes, neutron stars, or, critically, vast numbers of faint, distant brown dwarfs and rogue planets that inhabit the galactic halo. If Nemesis were one of these machos, it would make it a singular example of a dark matter particle captured in our solar system's orbit. The open scholarly debate here has largely dismissed the idea of Nemesis being a macho because surveys like WISE proved there aren't enough brown dwarfs close to us to account for the necessary gravitational effects of dark matter in the galactic halo. A mainstream historical fact is that the existence of brown dwarfs was only conclusively confirmed in the mid-1990s, well after the Nemesis theory was proposed. Since then, the T dwarfs and Y dwarfs, the coldest classes of brown dwarfs, have become the target of intense scrutiny. These dwarfs are so cold that Nemesis, if it's a Y dwarf, could be as cold as room temperature, emitting almost no detectable light, existing just as a massive, silent orbiting gravitational anomaly. This version of Nemesis is the darkest, quietest threat of all, not a star that is merely dim,
but a star that failed to ignite. The conflict is thus transformed. It's not a struggle against a known star, but against the sheer, silent mass of something that barely qualifies as starlight, proving that in space, silence is often the loudest warning. The brown dwarf theory makes Nemesis's invisibility plausible, but it also links its existence to the very edge of our cosmic knowledge. It's time to see if this deep, silent threat left clues in our past. You've explored the scientific theory of Nemesis, a dark twin driven by physics and periodic extinctions. But now you step back, letting the eerie quiet of the night suggest a deeper connection. Could the fear of a second, sinister sun be woven into the very fabric of human history and mythology? You're looking for evidence of the Nemesis conflict in historical accounts of celestial duos. The curiosity here is whether the memory of a past, catastrophic visit from Nemesis could have been passed down through oral traditions, becoming the cosmic myths we read today. If Nemesis last plunged through the Oort Cloud millions of years ago, no human witnessed it. But perhaps the instability caused by an earlier, smaller body, or the lingering trauma of a smaller comet shower found its way into ancient narratives. A mainstream historical fact is that many ancient cultures meticulously tracked the movements of stars and planets, leading to complex astronomical systems. However, some of these systems include celestial objects or alignments that modern astronomy can't easily account for. Consider the notion of the wormwood star found in the biblical book of Revelation. It describes a star falling from the sky, turning a third of the waters bitter and causing death. While almost universally interpreted as metaphorical, some fringe thinkers have applied the idea that this passage and similar apocalyptic visions across different cultures might be the distorted, mythologized recollection of a great comet strike, a single, massive icy body perhaps knocked into the inner solar system by the gravitational shake of Nemesis. Ancient cultures across the globe were obsessed with the idea of celestial balance and duality. Egyptian mythology. The Egyptians focused heavily on the sun god Ra, but he was often accompanied by the terrifying forces of chaos, notably the serpent Apophis, who attempted to swallow the sun during its nightly journey. This could be viewed as a metaphor for the periodic, destructive forces that threaten the cosmic order symbolized by Ra. Mesoamerican traditions. In certain Aztec and Maya myths, the current world is just one in a series of eras, each one destroyed by a great cataclysm, flood, fire, or wind before the next sun rose. The idea of a cyclical destruction, where a previous sun is overturned by a violent force, mirrors the Nemesis cycle of stability and reset. The open scholarly debate revolves around the interpretation of ancient proto-astronomy. Did these cultures actually observe and record astronomical events, or were their narratives purely symbolic? For example, traditional archaeology dismisses the idea that megalithic sites were oriented toward a slow-moving, distant object, yet the fringe theory persists. The key insight is that the legend might not record the dim star itself, which is too slow, but the terrible, repeating consequence it generates, a sudden, unexpected influx of destructive, watery, or fiery stars falling from the sky. The legend is the payoff of the hidden star's passage. The historical accounts, taken as a whole, transform Nemesis from a sterile mathematical concept into a primal, ancient fear. It is the deep human knowledge that even the brightest light, our sun, can be accompanied by a dark, destructive twin, a force of retribution that ensures no era of peace lasts forever. You've tracked the cosmic ghost Nemesis across its theoretical orbit and seen the mythological fear it inspires. But before we surrender to the darkness, we must remember the relentless, methodical effort to unmask this faint, slow-moving shadow. The conflict now shifts from theory to technology. How are modern astronomers actively trying to find Nemesis? The drive to find Nemesis fueled the creation of instruments specifically designed to penetrate the darkness and look for heat. You already know about the Wide-Field Infrared Survey Explorer, WISE, which put on those specialized heat-sensing goggles and mapped the entire sky 4 times over. The payoff of the WISE mission was not finding Nemesis, but severely limiting where it could hide. By ruling out large swaths of the sky, WISE proved 2 things. First, Nemesis is not a typical bright red dwarf star closer than about 10,000 AU. Second, it must be a much colder and dimmer object, an ultra-cool brown dwarf like a white dwarf, or a very low-mass red dwarf. It is likely currently at its aphelion, farthest point, and therefore moving at its slowest and radiating its least heat, maximizing its camouflage. This led directly to the next generation of visual surveys. The Pan-STARRS Panoramic Survey Telescope and Rapid Response System, operating from Hawaii, surveys the sky in visible light, specifically hunting for near-Earth objects and anything else that moves. While Pan-STARRS primarily focuses on closer objects, its deep sky surveys are also excellent for detecting any object with measurable proper motion, that slow, telltale creep across the background stars. It is, in effect, searching for the movement of Nemesis, even if it's currently optimized for the slightly closer gravitational mystery of Planet 9. A mainstream historical fact that validates this approach is the earlier similar theoretical search for Tyche, a hypothesized gas giant in the Oort Cloud. Tyche was largely ruled out by the comprehensive high-resolution data provided by WISE, showing that these all-sky infrared surveys can effectively dismiss major theoretical outer solar system bodies. The most exciting tool on the horizon is the Vera C. Rubin Observatory in Chile. Once fully operational, it will conduct the Legacy Survey of Space and Time, LSST, which will create an astronomical movie of the entire visible sky every few nights for a decade. This continuous monitoring is the perfect way to find Nemesis, particularly if it's a faint object moving slowly. The open scholarly debate remains. Should we be searching specifically for the dim light of Nemesis, or should we be looking for the gravitational effects it has on distant objects? Many scientists argue that detecting Nemesis directly is a needle in a haystack scenario, and a better strategy is to search for its shadow, the subtle gravitational perturbations it imposes on the known orbits of objects. The search is an active, ongoing mission. It is a slow, methodical grind against distance and darkness. Every time a new faint star or brown dwarf is cataloged, the chances increase that Nemesis is either ruled out or finally definitively found. The dark star might be sleeping, but the astronomers are awake.
You've tracked Nemesis across its theoretical orbit and seen the tools we use to hunt for it. Now, you must face the conflict at the heart of the theory, the moment of closest approach. What happens when Nemesis, after its multi-million-year journey, finally swings in to make its pass and the comet shower begins? The passage of Nemesis is not a quick event. It's a slow, gravitational tidal wave that takes hundreds of thousands of years to fully unfold. As Nemesis, the dark dwarf, approaches its perihelion, its closest point to the Sun, perhaps 30,000 AU out, the Sun's gravitational grip on the outer Oort cloud weakens relative to the incoming star's pull. First, you would see the astronomical warning. Long before the star itself is visible to the naked eye, its presence would be confirmed by astronomical surveys like the Rubin Observatory. Its proper motion would finally become clear, and its deep infrared signature would be catalogued.
We would finally know exactly how far away it is, how massive it is, and, most critically, its precise trajectory. This confirmation, perhaps a million years before the worst effects are felt, would be the greatest discovery and the greatest dread in human history. As Nemesis passes, its immense gravity acts like a colossal, invisible hand, shearing away the gentle, circular orbits of the Oort Cloud comets. The comets are flung inward along hyperbolic and highly eccentric paths, aimed directly at the center of the solar system. The payoff is the comet shower itself, a phenomenon that could last for 2 to 3 million years. It wouldn't be a constant rain, but a massive, sustained increase in the rate of incoming long-period comets. Instead of a typical rate of one major impactor every 10 to 100 million years, that rate could accelerate to one every few 100,000 years, or even more frequently. Imagine the curiosity of those future generations. They would live under a sky where the threat of a major global-scale impact is not a remote statistical possibility, but a known generational risk. Detecting and tracking every one of these icy mountains would be an overwhelming challenge for planetary defense systems. A mainstream historical fact that grounds this fear is the Tunguska event of 1908 in Siberia. While it was likely a small asteroid or comet fragment that exploded in the atmosphere, it flattened 2,000 square kilometers of forest. Now, scale that up. Imagine an impactor 10 kilometers wide, striking every few 100,000 years. That's the scenario Nemesis promises. The open scholarly debate here centers on the duration of the shower. How quickly would the excess comets be cleared out by the Sun and the gas giants? If the shower is short and intense, the chance of a civilization-ending strike is lower. But if the shower drags on for millions of years, it represents a state of near-permanent planetary vulnerability, a sustained period of extinction pulses. Nemesis's passage isn't just about the extinction of one species, but the prevention of long-term stability. The next time it swings by, we will have a front-row seat to the planet's gravitational master of doom.
You've tracked the comet to its inevitable, terrifying conclusion. The final conflict in the Nemesis narrative is the transition from a distant, cold theory to a physical, fiery reality, following a single projectile on its devastating journey to Earth. This is the final, intimate moment of the Nemesis payoff. Imagine a comet, a colossal, dirty snowball, perhaps 5 kilometers wide, sitting inertly in the deep cold of the Oort Cloud, 50,000 AU away. Its orbit is stable, gentle. Then, Nemesis makes its pass, and this icy body gets a powerful gravitational kick. It's knocked into a new, highly eccentric orbit aimed directly inward toward the Sun. This long-period comet begins its descent. It takes hundreds of thousands of years to cover the distance, slowly accelerating as it approaches the immense gravity well of the Sun. It passes through the Kuiper Belt, past Pluto, Neptune, and Uranus. At this stage, it's still a dark, cold object, barely detectable. It's a mainstream historical fact that these long-period comets often travel on paths that are highly inclined, meaning they don't stick to the plane where the planets orbit, but plunge in from above or below, making them incredibly difficult to predict or intercept. The curiosity now is that as it gets closer to the Sun, say past the orbit of Jupiter, its icy components begin to sublimate, turning directly from solid ice to gas. This forms the comet's characteristic coma, the fuzzy head, and the brilliant streaming tail. This is the moment the threat becomes visible, a magnificent, terrifying sword hanging in the sky.
The final hours are the most intense. The comet has survived the gauntlet of the gas giants and is on a collision course. When it hits Earth's atmosphere, likely traveling at 50 to 70 kilometers per second, over 150,000 miles per hour, the sheer kinetic energy instantly turns the air in its path into plasma. The resulting impact is catastrophic. The conflict is the difference between a rocky asteroid and an icy comet. Because comets contain high amounts of volatile compounds like frozen water, methane, and ammonia, the impact releases massive quantities of water vapor and gases into the atmosphere. This material not only contributes to the immediate dust cloud, but the water vapor, a potent greenhouse gas, can also cause longer-term climate effects, potentially leading to a sharp, confusing shift between impact winter and subsequent rapid global warming. A fringe tidbit about comets is the theory that they may have been the source of most of Earth's water, seeding the planet during the Hadean Eon. So the very objects that might have given us life are now being weaponized by Nemesis to take it away. The open scholarly debate here is about the extinction mechanism itself. Is it the dust and darkness, the acid rain from sulfur in the impactor, or the subsequent climate chaos that kills most life? When a Nemesis-driven comet shower occurs, it likely provides a deadly combination of all three, ensuring a wide-scale ecological collapse. You feel the comet's final violent approach, a silent, icy mountain accelerating toward the fragile atmosphere. The journey is nearly over, and the consequences of Nemesis's distant gravitational nudge are about to manifest in the most brutal, final way possible. You've tracked the comet to its inevitable, terrifying conclusion. The final conflict in the Nemesis narrative is the transition from passive victim to active participant, preparing for the cosmic threat. If the dark twin is found and its orbital path confirms the next comet shower is inbound, what can humanity actually do? This is the field of planetary defense, a growing area of science and engineering that moves beyond astronomical observation into existential risk mitigation. The payoff of finding Nemesis is the gift of time, a warning that might arrive millions of years before the worst of the impact shower. The first and most critical step is the detection and tracking of the incoming comets. While Nemesis itself is too far away to hit us, the comets it unleashes are the direct threat. The challenge is the sheer volume and the speed of these long-period visitors. A single comet takes hundreds of thousands of years to arrive, but a Nemesis shower means millions of comets are perturbed, requiring constant vigilance. A mainstream historical fact is that global efforts are already underway for near-Earth asteroids. NASA's Planetary Defense Coordination Office is constantly cataloging near-Earth objects. The Nemesis scenario introduces a threat from the extreme outer solar system, forcing a massive scaling up of deep space surveillance. Once a threat is confirmed, the goal is deflection, not destruction. You don't want to blow up a 5-kilometer comet. That would just create a deadly spray of smaller, radioactive, and equally fast-moving fragments. The aim is to change its velocity by mere centimeters per second, years in advance, so that by the time it reaches Earth's orbit, it misses by a planetary margin. The most viable deflection methods are kinetic impactor. This involves crashing a large, fast-moving spacecraft directly into the threat to impart a momentum change. The DART mission, Double Asteroid Redirection Test, successfully tested this method on a small scale in 2022, proving that humans can measurably shift an object's trajectory in space. Gravity tractor, a less violent and potentially more effective method. A massive spacecraft would fly alongside the comet for years, using only its own small gravitational pull to gently tug the comet off course. It's a slow, steady adjustment. If Nemesis is found millions of years in advance, the sheer timescale would introduce a curiosity for future generations. They would have the unique, terrifying mission of engineering a sustained multi-million-year defense plan. The open scholarly debate then becomes one of ethics and resource allocation. When you have a million years' notice, how much of your civilization's resources do you devote to a threat that is not immediate? This would be the ultimate version of the argument about prioritizing long-term survival over immediate societal needs. A fringe tidbit suggests that if the threat is too massive or discovered too late, the ultimate form of planetary defense would be self-relocation. Humanity might have to abandon Earth and move to orbital colonies or terraform Mars, using the gas giants Jupiter and Saturn as gravitational shields. Nemesis, the symbol of cosmic inevitability, ultimately forces us to become masters of our own destiny. The warning it provides might be the most valuable, terrifying gift we could ever receive.
You've traced the Nemesis theory from its statistical origin to the terrifying scenario of an incoming comet shower and the possible defense strategies. Now, as the quiet returns, you must ask the final question, the one that governs all your nighttime fears. Is Nemesis a scientific ghost story or a ticking clock? You are sitting in the quiet aftermath, and the payoff of this journey is the necessity of weighing the evidence, embracing the profound uncertainty that defines the scientific frontier. The conflict here is between the elegance of a theory and the difficulty of empirical proof. The periodicity. The original, compelling argument remains the 27 million year cycle found in the mass extinction and major impact crater records. The regularity is difficult to attribute to purely random events. An external, orbiting gravitational clock provides the most elegant explanation for this rhythm. The binary norm. Statistically, our sun is more likely than not to have a binary partner. Nemesis, even in its extremely wide orbit, brings our star into line with the galactic norm of multiple star systems. The Oort Cloud mechanism. We know the Oort Cloud exists, and we know its icy contents are only weakly bound to the sun. We also know that passing stars do perturb it. Nemesis simply provides a massive, regular, and predictable perturber. A mainstream historical fact that lends credence to the idea of undiscovered massive objects is the historical context of planetary discovery. The discovery of open scholarly debate in 1846 was based purely on calculations of its gravitational effect on Uranus. It was found before it was ever seen. The missing star. The most damning evidence against Nemesis is the lack of direct observation. Powerful, all-sky infrared surveys like WISE have essentially ruled out Nemesis as a typical red dwarf or brown dwarf closer than about 10,000 AU. The statistical weakening. As dating techniques for craters and extinction boundaries improve, the strict 27 million year periodicity has weakened in some analyses. The clustering might be less neat than originally claimed, making the need for a precise orbital clock less critical. The orbital instability. The Nemesis orbit, at 50,000 to 100,000 AU, is incredibly vulnerable to being ripped away by the galactic tide or by passing stars. Orbital dynamicists argue that Nemesis should have been gravitationally unbound from the Sun billions of years ago. The open scholarly debate boils down to this: what is the true origin of the long-period comet showers?
If they are not caused by Nemesis, then they must be caused by the Sun's periodic passage through the denser regions of the Milky Way's spiral arms, which offers a less regular but still plausible mechanism for stirring the Oort Cloud. The curiosity Nemesis represents the deep human knowledge that the universe is not safe. Whether the dark twin is an orbiting fixture, a ticking clock, or a recurring random visitor from the galaxy, a statistical ghost, the message is the same. The deep, dark reaches of space hold massive objects whose existence and movements directly influence the survival of life here on Earth. The Nemesis theory simply gave a name to the fear inherent in our lack of cosmic knowledge. You close your eyes, the last vestiges of that vast, empty cold fading away. The search continues, the telescopes scanning the infrared, looking for that faintest flicker of heat. Until it is found or completely ruled out, the theory of Nemesis remains one of the most elegant, terrifying, and persistent reminders that we are not alone, even in our solar system. The dark twin may be sleeping, or it may be a myth. But the fear it represents is very, very real.
You're letting go of the cold now, allowing the warmth of your own place to settle around you again. The stars are receding, not as a terrifying void, but as a vast, quiet ceiling of distant diamonds. It is so easy, isn't it, to think of the universe as a distant, abstract thing, full of clean numbers and predictable orbits. But tonight, you took a long, slow journey to the very edge of where our sun holds sway, realizing that even our own star holds secrets deep in its gravitational shadow. Let that uncertainty fade. Let the numbers soften. Whether or not the dark twin exists, whether or not the clock is truly ticking, your world is safe tonight. The pace of destruction in the universe is immense, measured in millions of years, not minutes. You are here now, grounded in the gentle, immediate present, protected by the long, deep rhythm of cosmic time. The search for Nemesis will continue, but you can let the intensity go. Your mind is quiet now, the images of the dark star and the falling comets melting away like ice. Let the slow, deep gravity of sleep pull you down, reassuring you that for this night and for many nights to come, our corner of the cosmos is quiet. Rest now. Sweet dreams.